All right, good morning, everybody. We'll start the recording. If you're here in person or if you're at home, go ahead and take a couple minutes to try these warm-up problems. Then we'll do them together and move on with the lecture. All right, let's get started. So today we're going to cover section 2.3. So section 2.3 is about a couple things. We're going to talk a little bit about some notation, meaning ways that we write down derivatives in mathematical language. And we're going to talk about tangent line approximation. Okay, so using tangent lines to approximate functions. And we'll have some problems, and that'll be it for today. So somewhat lighter on content. Make no mistake, though, these tangent line approximation things can be a little bit tricky. So let's start off with just the warm-up problem. Who can help me with part A? Anyone feel confident? This was subject matter for your exam. Yeah.
So first you have to plug in the x's to the equation to find the y.
Mm-hmm. And which ones should I plug in first?
I did the 1.
Okay. So we say that 1 is equal to b and 3 is equal to a. Perfectly fine if you do it that way. If you'd rather start with the end point on the other side, that's fine too. Thankfully, when we take the slope of a line, we can permute the points any way we want. By which I mean, if I have 2 points on a line, say this point and this point, it doesn't matter. It doesn't matter which one I call x1, y1, and which one I call x2, y2, because the negatives are going to cancel out. Okay, in one case we'll get a positive over a positive, and then in one case we get a negative over a negative. Okay, so we'll do it that way. So we get 2 times 1 squared plus 1 minus, big set of parentheses, 2 times 3 squared plus 1. And now what should I do? Solve it and then divide by something, right?
Yeah, just the 3 minus 1.
Exactly. Well, I got to be careful since I started with 1. That's got to be my b, so I got to do 1 minus 3. So if we solve this out, I don't know, we get something like hang on. So here we're going to get minus 18 plus 1 is 19. And then 2 times 1 squared, that's 2, plus 1 is 3. So we get 3 minus 19 over negative 2. So we get negative 16 over 2 equals negative 8. Is that what everybody else got? Cool. Okay, we'll fly through this one. We already know how to do these. So we're just going to plug in 2 times 2 squared. I usually like to use the right endpoint as my b, but that's just the way that I like to do it. If you want to use the left one, that's fine. So we'll do 2 times 2 squared plus 1 minus parentheses 2 times negative 2 squared plus 1, all divided by 4. And you'll notice that 2 squared and negative 2 squared are the exact same thing, and that you're going to get the exact same number here, and they're going to cancel out. So we're going to get 0 over 4 equals 0. What is it? Yes?
On the first one, should it be a positive 8 since we didn't?
Thanks. Yes, there was a negative 2 there that I missed. It should be positive 8. Thank you. Okay, so let me ask you guys, what does it mean if my average rate of change over an interval is 0?
There's no slope.
There is a slope. It's more like we would say the slope of the
rate of change.
The slope is 0 is what we would say. If I were to graph this, intuitively, I'm looking for some description of the height of these 2 points based on the fact that we know the average rate of change is equal to 0. Can anybody help me with that? Yeah, Ryan?
They both be on the same y-axis.
Exactly. They're going to be at the same height. Okay? So in this case, we have some parabola, for example. It looks like this, I think. Oops. Gotta keep doing that. I better move it down a little bit. Okay, so what it's telling us is that here at negative 2 and here at positive 2, the height of our points are exactly the same, which is why the slope of our direct path is going to be 0, aka a horizontal line. I think that's what you were getting at, Dylan. Okay. Any questions about those? I feel like we've had a lot of warm-up problems about average rate of change. Okay. So next up, we're going to talk about Leibniz notation. Interesting story, I guess, that you might not know. Isaac Newton and Wolfgang Gottfried Leibniz, I think is his name, both kind of simultaneously developed calculus in different parts of the world at the same time. And so they're both kind of seen as like the fathers of calculus. And to this day, there are people who tend to use Leibniz notation more than Newtonian notation, which is what we've been doing so far with the primes, like f prime of x. That's Newton's notation. Leibniz did it a little bit differently, and that's what we're going to talk about now, because there will be times where we talk about calculus using Leibniz notation for convenience sake, and there will be times that we talk about it using Newton's notation for convenience sake. So how do we describe Leibniz notation? So what Leibniz said was something like this. I know that the derivative of f, why don't I say of the function y equals f of x at the point A is given by taking the average rate of change of f of x on smaller and smaller intervals about A. Interval about A just means it's an interval which includes A. Okay, so we know that we get the derivative by taking this kind of limit argument where we take the average rate of change closer and closer and closer to our actual point. So the one way to express the formula for average rate of change is delta y over delta x, right? Where delta represents the words change in, right? Change in y over the change in x. This exactly says rise over run. Okay, that's what this says. Change in y over change in x. So as we take it really, really close, what Leibniz thought to say was, okay, well, we're not exactly taking the change over a reasonable interval. So he said, let's write the limit of this process as dy dx. Where d now represents infinitesimal change in. Okay, so meaning that we have taken this average rate of change around smaller and smaller and smaller and smaller intervals until the interval is not even a reasonable unit of length. We've taken the limit of this thing, and now we write it as little dy over little dx. And the reason that it's a little d here and not a little delta is delta's used in a lot of other mathematical contexts that would make it inconvenient to write it here. So if you don't know, this big triangle here is a capital delta in like Greek letters. So this d here is kind of like the lowercase version of it, is what it's meant to represent here. Okay, so we got big changes, or we use a capital delta. For infinitesimal changes, we use a lowercase d. I think that's as concisely as I can put that. You'll become much more familiar with Leibniz notation as we go on. So first of all, I should also say that this is going to be equal to f prime of x. Okay, so when I write dy dx, I mean f prime of x, or g prime of x, or h prime of x, depending on the function. Are there any questions about Leibniz notation so far? I think it might get easier if we do an example. Okay. The power output, P of W in megawatts, is a function of the wind speed W in miles per hour. So we're supposed to write P prime of W in Leibniz notation and give the units. So what do we think Leibniz notation should be for P prime of W? Yeah, Kevin?
Would be dP of W over d of W.
Correct. We would say this out loud. We would say dP dW. That's usually how we say that. So when I say dP dW, I mean dP over dW. So thank you, Kevin. So let's talk about the units. Now remember, the derivative represents change in the top thing based on change in the bottom thing. Okay, so the units here are going to be, let's see, megawatts per mile per hour wind. Okay. Let's try problem 2. Sam's puppy Meatball. Well, maybe I should let you guys keep writing. You guys done? Okay, Sam's puppy Meatball has a weight function, W equals G of T, where W is in pounds and T is Meatball's age in months. Okay, so think of time T equals 0 being the day that the puppy is born. Okay? So, do we expect G prime of T to be positive or negative, and why? Anybody want to help me with that one? Yes, Michael?
Positive because the weight's increasing.
Exactly. So from the question, we can kind of infer that a young puppy, over the first few months of its life, is going to cultivate mass, so to speak. So the weight of the puppy is going to increase. We know that if we have G should be increasing, therefore G prime should be bigger than 0, at least initially. Okay, let's write the derivative in Leibniz notation. So we're given W equals G of T. Okay? This is a little bit different than the previous example where there's kind of implicitly a P equals P of W is kind of what's going on in this case. For this case where we have W equals G of T, we want to refer back to our situation where we had Y equals F of X. When we had Y equals F of X, we said that F prime of X is equal to dy dx. So what goes on top should be the variable which represents the output of our function, okay? And the bottom should represent the input of our function. So in the case of problem number 2, we had the output letter was the same as the letter that we used for the function. So that's why when I wrote dp dw, this P here came from the left-hand side. the letter that we're using for the output. Okay, I don't want to confuse you and make you think that it's coming from the letter which we use for the function. So the way that we're going to write it on this one, since we have the output as weight and the input as time, I'm going to write the derivative as, we could write it as g prime of t, or we could write it as dw dt. Okay, and what are the units of g prime of t? Well, it's going to be change in pounds per month. Okay, those are going to be our units, pounds per month. Okay. Did I lose anybody with this talk about the inputs and the outputs? Okay, I guess not. Then we'll move on. All right, we're supposed to interpret g prime of 8 equals 6 in the context of this problem. So we know that our input is 8, our output is 6, and the function is the derivative, which represents instantaneous rate of change. So who can help me figure out what this really means in words for the problem? Anyone feeling confident? Ryan?
I bet like in 8 months he gained 6 pounds.
Not quite. That would be true if we were taking the average rate of change from 0 to 8. So the answer that Ryan gave was that in 8 months, the puppy gains 6 pounds. That's on the right track. It's representing our 6 here as a rate of change. However, g prime of 8 is really referring to the instantaneous rate of change. So the way that we would interpret this is in terms of the instant of t equals to 8. Meaning, in the 8th month, the puppy was growing at a rate of 6 pounds per month. Now, it's a little bit confusing when we make a statement like this, because when I say in the 8th month, what I really mean is on the last day of the 8th month, at the last second of the last minute of the last hour of that day. What I mean is instantaneously at the end of the 8th month, the puppy was growing at this rate. And it could be that the next day, the rate at which the puppy was growing increased dramatically. So it's not necessarily to say that from the start of the 8th month, from the end of the 8th month to the end of the 9th month, the puppy gained 6 pounds. That's not necessarily what this is telling us. This is just telling us what the slope of the tangent line was at that point. So let me kind of draw what I mean here. I'm going to add an extra page. And we'll use clear paper. Okay. So what do I really mean? If we were to draw time on this axis and weight on this axis, well, the puppy might start at like, I don't know, 5 pounds or something like that. And then it's going to grow really fast, and then it's going to kind of slow down, right? And then maybe it'll bottom out at like 20 pounds if it's a small dog. What I'm saying is that this is time t equals 0, right? And this is 8. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8. What I'm saying is, at this exact moment, after exactly 8 months have passed, the slope of this tangent line is equal to 6. That's what I'm saying. What I'm not saying is that from 8 to 9, we're going to grow at exactly that rate. Because as you can see, our tangent line doesn't exactly correspond with the way that our function is going. It's only a good description of how quickly we're growing at that particular moment in time. Okay, so we only care about this moment in time 8. That's all we can say. So really, what I should say here is not in the 8th month, but rather at the end of the 8th month. The puppy was growing at this rate for that infinitesimal unit of time. Okay, assuming that Meatball is healthy, what do we expect the value of g prime of 36 to take, and why? Take a couple seconds to think about that. We want to think about g prime of 36 here. Anybody have a dog? Anybody have a big dog? How big's your dog? Yeah,
She's like 90 pounds, I think.
90 pounds. Anybody beat 90 pounds? How long did it take for your puppy to get to 90 pounds?
I have no idea.
Maybe a year or 2?
I don't remember. I got her in 3rd grade, so I don't remember.
We got my puppy for like 6 months and now he's 70 pounds.
Oh man, that's a big boy. So he's gonna grow a bit more. Yeah. Okay, but at what age do we expect a dog to be more or less full grown? Maybe 2 years. And once a puppy's full grown, if they're healthy, are they gaining or losing weight? Or neither? Probably neither, right? So if a puppy is 36 months old, they're 3 years old, how do we expect their weight to be behaving from day to day? Not a trick question.
They maintain their weight?
Yeah, they're maintaining their weight. So if their weight is neither increasing or decreasing, what can we say about g prime of 36? Yeah, Kevin?
Is it equal to 0?
Yeah, it should be equal to 0. Okay. Let's go back to our graph and see why that's true. Our graph said we started out at 5 pounds, and then we started growing, and then here's maybe, let's add some more x values on our x-axis. We've got, here's like 16, right? And dot, 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 maybe like way out to the right, we've got 36. So if we were to keep drawing this, it would look kind of like that, right? So the puppy grows, and then it hits its maximum weight. And then after that, it pretty much just stays the same weight for the rest of its life, assuming that it's a healthy dog being fed by responsible owners. So the slope of our tangent line, if we were to take a tangent line right here, it's gonna just be a horizontal line, right? That's how we're gonna draw that. Okay, so that's what's happening on the graph. Okay, so tangent line approximation, we're going to talk about now. Here's how I want to describe it to you. First, I'll tell you what a tangent line is. A tangent line is a line that behaves in a special way, which intersects the graph of f of x at x equals a and at no other point very close to x equals a. So what do I mean? I'll do another drawing. So we might have a tangent line at this point here, which is x equals a. So this is the point a comma f of a. And our tangent line will look something like this. See if I can straighten that out. Come on, straighten. Oh, all right. It'll look something like this, right? So what it does is it comes in and it just barely kisses the graph, and then it goes off again. Now I want to draw some attention to the part of the definition, which I'm going to underline now, that says, and at no other point very close to x equals a. Okay? That's to say that in some small interval about our point, there's no other intersections. Okay, so it's just coming in, it's not going through our graph. It's just coming in and just barely touching it and going off on the same side. Okay? However, it's okay for this tangent line to intersect our graph again, say, very far away, like over here. That's fine, okay? But very, very close, we want it to be away. This is kind of just like how I'm trying to capture the definition of what a tangent line is really doing, okay? So it's just coming right up, touching it, and moving on. And it's a fact that if our graph is curvy like this, there's only one line that's going to satisfy this property, okay? Any other lines are going to either intersect multiple times, or they're going to pass through, or they're going to not touch it at all. Okay, so that's what a tangent line kind of is. And here's what we want to use them to do. We'll use purple. Near, let me quantify what is near. When x is very close to a, f of x is very close to t of x, where t is the equation of the tangent line. Okay, let me go back to my drawing now and explain what that part means. What I'm saying is that at this point, I know that the tangent line is equal to the function itself. And I know, at least at first, that it's headed in basically the same direction as the graph of f of x. So if I want to know the value of f of x at this point right here, well, I know that a point that's very nearby is going to be this point here on the tangent line. So as long as I'm very close to this point A, by which I mean the x values are maybe in some interval about it, then I know that the tangent line and the function are going to be pretty close to one another. You know, the further I go out, the worse it gets, right? If I take this point versus this point, well, it's not a very good approximation at all. There's a huge error. But when I'm really close, the error will be small. Okay, that's what's going on with the tangent line. So let me write down an equation for this tangent line. The way we would write it is f of a plus f prime of a times x minus a. Okay, the way I got that equation, by the way, is just by using point slope form. Okay. All right, so the point is, if I want to know what f of x is, then I can just plug into this thing instead. As long as x is very close to a, it'll be a pretty good estimate. That's the upshot. Okay, let's do some practice. All right, fertilizers can improve agricultural production. A Cornell University study on corn production in Kenya found that the average value y equals f of x in Kenyan shillings of the yearly maize production from an average plot of land is a function of the quantity x of fertilizer used in kilograms. Okay, so our input here is x, the number of kilograms of fertilizer that we used on our plot. And our output here is going to be y, which represents $1 Kenyan, basically. Okay, they call it a shilling. Okay, so now we're supposed to interpret these statements. F of 5 equals 11,500 and f prime of 5 equals 350. Before we do that, let me ask you, how would we write f prime of x in Leibniz notation? Kevin?
Would be d of y over d of x.
Exactly, we would write dy dx. Exactly, because our output is y, we know that on the top we should have infinitesimal change in output, and on the bottom we should have infinitesimal change in input. That's where we get our x from. Okay, so this is how we'd write it in Leibniz notation. All right. We want to interpret the statements f of 5 equals 11,500 and f prime of 5 equals 350. So we know that our input is 5 and our output is 11,500. That's saying if I use 5 kilograms of fertilizer, I will make 11,500 shillings. Okay. Now remember, our derivative represents the instantaneous rate of change. Okay? The instantaneous rate of change. So what this part says in pink here is when the input is exactly 5, the slope of my tangent line is 350. The way we interpret this statement is when we let me say this in a better way. I want to give you a proper statement here. Man, how do I want to say this? Okay, so when using 5 kilograms of fertilizer, increasing the fertilizer amount increases our money earned at a rate of 350 shillings per kilogram of fertilizer. That's what it's saying. Okay, so we got to go back to that idea that we were having about the puppy, right? We were wondering, how is the weight of the puppy changing at the exact moment of time which corresponds to the end of the 8th month? What we're doing now is we're saying, how is our earnings changing at the exact moment that the number of kilograms of fertilizer we're using is 5. Now, in both cases, there's an implicit assumption that the independent variable, being our input, is increasing, right? We think of time as typically going forward, right? So we say, how is the weight changing as time is going forward? We say, how is the amount of money we're earning changing as the amount of fertilizer increases, right? So our independent variable, when we're talking about these derivatives, we always think of it in the reference of saying that our independent variable is increasing. Okay? All right, we're supposed to use the statements in part A to estimate f of 6 and f of 10. So the way we're going to do that is by using our tangent line approximation. So let's have a picture of what's going on here. We have a graph where here is our kg of fertilizer, aka x, and here's y, our amount of money. Initially, I'm assuming if we use 0 fertilizer, we probably don't make very much money. And as we use more, we go up and up and up. What we really know here is just the fact that at 5 kilograms, we know that we make 11,500. So 11.5K is here. And we know that the slope of our tangent line at that point is 350. Okay, so maybe it looks something like this. Here's our tangent line. As for what the graph of f of x actually looks like, let's just say we don't know. We don't know what f of x actually looks like. Okay, so I'm going to draw a couple things that f of x could look like on here. We'll do one with green. Maybe it looks something like this, kind of diminishing returns the more kilograms we use. Or maybe the more fertilizer we use, it just keeps getting better and better. And maybe it looks something like this. Okay, but what this tangent line approximation thing is saying is that if I just consider what's going on inside this yellow circle, very close to this point, the value of the red line is pretty close to the value of the pink line and the green line. Okay, so it doesn't really matter that we'd have no clue what f of x actually looks like. We're just going to say that, well, I know what the tangent line looks like, and I know that very close to this point where we have the tangent line, the function is going to be relatively close to the point on the tangent line that corresponds to that x value. Okay, so that's really what we're doing here. So let's come up with the formula for the tangent line. Remember, we wrote it down as f of a plus f prime of a times x minus a. I'm going to just plug that right in. So I know that f of x will be approximately t of x, which will be equal to f of a plus f prime of a times x minus a. Since we know what f of 5 and f prime of 5 are, we can write this down as 11,500 plus 350 times, this should be x minus 5. Okay, so I just got that from the fact that a is 5. We know what f of 5 is, and we know what f prime of 5 is, so I just plugged into my formula. This is the equation of a line. It looks like b plus, well, it looks kind of like b plus mx. We've got this little 5 in here. We'd have to distribute it out to get b itself. But this is the equation of a line, and now we're just going to plug in 6. Okay, we're just going to plug in 6. So we get f of 6 will be approximately, that's what these squiggly lines mean, 11,500 plus 350 times 6 minus 5. Well, 6 minus 5 is just 1, so this is going to be 11,850 shillings. F of 10 is going to be approximately 11,500 plus 350 times 10 minus 5. So 350 times 5, I think we'll get something like 13,250 shillings. Okay, so we estimated. And here's the really important part that I want to drive home. It has to do with this part C here, okay? Which estimate in part B is more reliable? Let's have a show of hands. Who thinks that the estimate for f of 6 is more reliable than f of 10? Is there anyone who thinks otherwise, that the estimate at f of 10 will be more accurate? Okay, for those of you who said that we think that the estimate at f of 6 will be more accurate than at f of 10, can you explain why you think that? You're right. Someone besides Kevin? Kevin's been helping me out all day. Yeah, Wyatt.
The deviation when you add another x value would just keep increasing.
Exactly. In short, what Wyatt is kind of expressing here is that 10 is further away from 5 than 6. 10 is further away from 5 than 6. So if we were to look at our graph here, we'll draw on 6 and we'll draw on 10. When we're at 6, we know that the difference between these three curves can't be too large. So the estimate will be pretty good. The further out we go, the difference between these curves might be huge. Okay, if we were to extend these like this, and who even knows what the pink thing is going to look like. So this distance now is really large. okay? So the estimate with f of 6 is going to be a better estimate. So f of 6 is more reliable, since 6 is closer to 5 than 10 is. Okay, I think that's all we got time for today. If you have any questions or you want to see an extra problem or something, you can hang out after class.
Is this a sheet posted somewhere different? Because I didn't see it.
Sorry?
The note sheet. I didn't see it.
Ah, no, the note sheet was not up today.
Oh.
Thank you. I knew I was forgetting something. Okay, I'll get it up for
No.
Friday.
Thank you.
Yep. Ryan, question?
So f of a is pretty much just like what f of x equals.
When x is equal to a, exactly.
Yeah, okay.
So when I write f of x, I'm referring to x as my variable. When I write f of a, I'm kind of thinking as if a were actually some number. In our case, for this problem, a was equal to 5. So that's why when I put in this formula here for t of x, I did f of a plus f prime of a. I exchanged those for f of 5 and f prime of 5 because I was letting a be an actual number itself.
But so here like in f of a in the example, that's like the y value of like that coordinate, right? Like the x value would be 5, and then the y, like the amount of shillings would be 11,500.
Yeah, exactly. So that just goes back to like what a graph looks like, right? So if I have a graph, what I say is that y equals f of x, okay? So if I have an x value here, a, when x equals a, that's telling me that the y value of this graph here equals f of x equals f of a. So I just get the y value of the function by taking whatever number is here and plugging it into this function, and then I make the height of my function that value. So this point here would be the point a comma f of a. So
It's like having an x in the equation,
Mhm.
also like with like what would normally be
yes.
x.
Yeah.
Threw me off.
Oh yeah, that's a great point. Okay. So what needs to be said here is that t of x is an entirely different function. It also takes x as an input, the same input that this function f of x takes. However, it's a different function. It's a function which is a polynomial. The constants of the function are given by plugging in numbers into this f of x function. So this right here, f of a, f prime of a, and a are all just numbers, okay? And x means exactly what you think it is. It means some value on this axis here, okay? So the height of the t of x function is given by taking this number and adding it, so this f of a number, and I add it to this number f prime of a times the value of x, which I'm at, which may be given by this point right here. And I subtract it from a, so this kind of looks like the distance between.
So what is, when it does, I get the f of a and f prime of a, what is the a and x minus a?
So exactly, so that's kind of what I'm talking about right now, is it's the distance here. It's the distance between a and my x value. Okay. So in particular, if x is really close to a, then this number x minus a will be really small. And so when we multiply it by f prime of a, it's not really going to change much from f of a. The fact that it's not changing too much is exactly why the tangent line is a decent approximation when x is really close to our point a.
So A is like the actual like one and X is like the approximation one?
Yes, so exactly. So we know what f of a is. So we're not interested in knowing what f of a is because that's already a known value. What we're interested in knowing is the value of f of x near a, which for us is complete guesswork at this point. Okay, we have no idea what the function actually looks like. We only know the value of f at that point and the value of the derivative at that point, which is a very incomplete picture of how the function actually looks. But what we can do is draw this tangent line and then say, I am able to find out the value of the tangent line near this point, even though I know nothing about the value of f near that point. However, I do know that f is generally at the same point and going in the same direction as this tangent line, so nearby, I hope, it'll be a similar value.
And that value is x in this case, right?
And that,
Like that
the value is, so the value is, I know what f looks like at this pink point. I want to know what f looks like at this pink point. I want to know, is that pink point there, or here, or here, or here?
Yeah, and like that second pink point, isn't that x or no?
The pink point is the point x comma f of x.
Okay, yeah.
So on the x-axis, I would put an x here.
Yeah, okay.
So the x value is exactly the point in x space where I'm hoping to know the height of the actual function. I estimate the height of the actual function, which is this, I'm running out of colors, this purple point here. I estimate this height here by instead estimating the height of my tangent line. And the guarantee is that if this brown distance is pretty small, the blue distance will be very close to the purple distance.
Okay, yeah, I think I get it now.
Mhm. Yeah, so there's one thing that I want to point out, which is that x always is representing a point in space on the x-axis. Okay, that's what x is representing. What x minus a represents, this part right here, x minus a, what that represents is the distance between,
The very close point, right? And
that represents this brown distance here, the distance between those 2 points.
Okay. Alright. I get it.
Okay, does that help?
Yeah, thank you very much.
All right. Derica, did you have some questions on the material for today, or you want to talk?
This is a question about my grade.
Oh, okay.
I don't have the grade for my 1.7 exit.
For 1.7 axis slip. Okay, can I look into it when I get home and I'll email you about it? Are you available via email?
Yes.
Okay. So it's just the 1.7 exit slip that you want me to check, or anything else?
Just the 1.7.
And you have a 0 in there, or you have no grade for it yet?
It's a 0.
It's a 0, okay. All right, I'll check it.